Okay, well, thank you for inviting me to speak. I'm going to talk to you about Zocalo, which is basically is behind the data analysis infrastructure for much of Diamond. Right, okay. So just to outline what I'm going to talk to you about, so first I'll just give a brief introduction to what is Zocalo and some examples of what it can do or what we use it for. And then I'll go into just a bit more detail about some of the implementation details behind it and where the various components run. And then I'll briefly mention a bit about how we monitor what's going on as well. So first of all, what is Zocalo? So as I mentioned, Zocalo is basically behind all of the data analysis infrastructure at Diamond. So it's made up of multiple components. So we build upon, it's made up of various components that we call services and wrappers, and they're tied together by recipes, and they communicate with each other via the transport layer, which is an abstraction on top of a message broker, such as we now use RabbitMQ, as I will mention shortly. So what can it do? So we use it for online analysis. So for example, spot finding from diffraction images, which can give us quick feedback on whether there's actually a diffracting sample in the beam or on the data quality, for example, in early indications of radiation damage and which not. Sorry, wrong way. Okay, we also use the parent analysis forms the basis of the X-ray centering for automated X-ray centering, so, which is a key component of the unattended data collection on the Diamond MX beamlines. We're also starting to make use of it to provide feedback for serial data collection. So again, that's with initially with the spot finding on each image, but we're also looking at adding indexing into that as well in the near future. Then in terms of offline analysis in the MX world, what we mean by that is running external programs like FastDP, ZO2, AutoProc, and so on. So they're all run, they're all orchestrated through Zocalo, and then after that we can potentially run further downstream analysis on, for example, phasing pipelines like FastDP, Dimple, Mr. Bump, and various other phasing pipelines that are run through Big EP. So just a brief diversion into message brokers. So what do we mean by message broker? So here I'm talking about something like RabbitMQ or ActiveMQ, and fundamentally that's just a bit of software that manages a set of queues that applications can connect to and send and receive messages. So you might have different applications that produce messages, and here a message can more or less be anything. It can be some text or a binary blob of data or anything, and that is published to a queue that's managed by the message broker, and then you can connect different software to that to consume messages from the queue. So why do we want to do that? Well, in this context, it means we can take advantage of asynchronous or delayed message delivery. So we don't need to be able to handle a message at the time it's been generated. It can allow us to, if we want to distribute a message to multiple consumers or to balance loads between multiple worker processes, and also making use of a message broker based system can help reduce the coupling between the senders and receivers of messages, and it can also give us improved fault tolerance, because we can make use of things like transactions to ensure that if we fail halfway through dealing with some processing, then we can potentially replay that. So we originally, when we implemented Zocalo, we started using ActiveMQ because that was used elsewhere at Diamond. But over time, as we started to use it, Zocalo more and more, and rely on it more with the unattended data collection, we started to see problems with that. So we've recently completed a project to switch to using RabbitMQ as the underlying message broker, and the reasons we chose that was because it has a wide user base and an open and welcoming development model, and it provides lots of excellent resources for users and administrators. So, for example, with various monitoring tools and so on, it allows us to make use of a rather flexible messaging topologies, which we're only beginning to scrape the surface of how we can use. So in terms of our implementation at Diamond, we have this set up as a redundant cluster of 3 RabbitMQ servers, which obviously gives us an added benefit over the previous ActiveMQ setup, where we had a single server, which proved a single point of failure. So now, just to go through some of the components of Zocalo. So first of all, I mentioned that we have a transport layer. So this sits as an abstraction on top of the message broker. So you're not dealing directly with the message broker, but you're dealing with the transport layer. So this implements support for RabbitMQ via the AMPQ protocol, and STOMP or ActiveMQ via the STOMP protocol. And having this made it easy for us to, made it easier for us to transition between ActiveMQ and RabbitMQ. And then, yeah, so as I said, yeah, the services and wrappers communicate via the transport layer rather than the message broker itself. So one of the main components are services. So here, a service is something that consumes a message from a queue and does something based on that message, and then it can optionally send output to another queue. So these are typically suitable for short-lived tasks. So this would be something like doing spot finding on an individual image, or inserting a single set of results into the database. So a service is essentially expected to be a long-running background task that sits around and waits for work to come in via the queue, that service subscribes to. And Zocalo itself is agnostic to where or how the services are run. So we've recently moved to running most of the services at Diamond and now run and orchestrated via Kubernetes. But whereas before we had some custom code within Zocalo that sort of handled the orchestration and ran the services as cluster jobs on our compute cluster. But you can have, you can potentially have either model or a mix as both as fits your use case. And then the other main component are wrappers. So these are generally used for longer running tasks. So something that would take on the order of like from several seconds to minutes or even hours, depending on the particular processing job. So in contrast to services, wrappers only run when needed. So in our case, it would typically be on an in-house computing cluster, or we've recently done work to be able to also take advantage of cloud compute provision via the SDFC. So they're intended to wrap something that isn't necessarily aware of Zocalo and shouldn't have to be. So something like ZIR2 or dials, they don't know anything about Zocalo, and this is basically a wrapper to enable you to run it through Zocalo. So a typical wrapper would take an input message and perhaps convert it to command line input, run the software, and then it will interpret the results and then potentially send an onward message back into Zocalo, so that would be maybe like with the results to be inserted into a database, for example. Okay, so we've got services and wrappers, and we've got a bunch of different services and wrappers for different programs. How do we link them together? So the queue, the particular queue a given service consumed from is relatively well defined. And most services that we have consume from a single queue. Some of them might consume from more than one queue, but it's usually a limited set. But then when we want to send onward messages to other parts of the components, how do we do that? I mean, we could hard code that information in the services, but that limits how flexible we can be. So we might want to be able to stitch together the services into different pipelines. So for example, here we use the file watcher. So this basically watches for files appearing on disk, so that we don't try and do processing when the file hasn't actually hit disk yet. But here we can reuse this in multiple pipelines. So this is where recipes come into Zocalo. So essentially, a recipe encodes the connections between services and wrappers, and where the services are connected in a directed acyclic graph, in which the nodes correspond to services and the directed edges represent connections between each service. And each node can have one or more input, and any node can have 0, 1, or many outputs. So you can see, obviously, if a node has 0 outputs, and that's the end of that part of the tree. Okay, so internally, a recipe is represented as a Python dictionary, where here in this case we've got three steps of the recipe, and this indicates where we start. So here this indicates that the first step of the recipe will be sent this string, some data, and then it will generate output that will then be sent to step 2, and step 2 itself can generate output that will be sent to step 3, and step 3 doesn't generate any output, and so that's basically the end of that chain. And independently, in this case, in this example, step 2 will also be sent a separate message, which containing the contents of this dictionary, and again that will send any output to step 3. So just as an example of a recipe here is in X-ray, as used in X-ray centering. Okay. So we have the file watcher service that is watching for the images, because we want to be able to do the parameter analysis as soon as the images are collected, rather than waiting until the end of the data collection. So we want to do that as soon as each image appears on disk. So we're watching for them arriving with the file watcher. For the first image, we generate a diffraction image preview that is used to display in SynchWeb, and then for every image that arrives, we send a message to the parameter analysis service, which does spot finding via dials. The results for that are sent to the I/SPY-B service, which then records the results for that image in I/SPY-B, and the results are also separately sent to the X-ray centering service, which then accumulates all of the results for a single data collection, and then eventually writes the results to a JSON file, which GDA is watching for. So just quickly to talk about where the services run. So we've recently used to running the majority of our services on Kubernetes, which gives us advantages like the automated rollouts and rollbacks of updates and automatic restarts of failed containers and so on, and also provides us things like service discovery, which is we can take advantage of as part of the monitoring. So we manage the deployment of Zocalo as a whole via a Helm chart, where each individual service is a standalone Helm chart that depends on a shared library chart, and then we've got a top-level umbrella chart that ties everything together, so you can deploy the whole stack with a single Helm command. And then in terms of monitoring, because we rely on this a lot now, especially for unattended data collection, we want to know, is everything okay? So here we can take advantage of the popular open source tooling like Prometheus and Alert Manager and Grafana, which can give us alerts when things go wrong via email and Slack, and again, we take advantage of running services on Kubernetes, which allows us to hook into the Prometheus service discovery. So we have a Grafana dashboard that we're working on to display some of the historic metrics as well. Okay, yeah, obviously there's lots of people at Diamond that have contributed to all this work, and you'll hear a bit more about how Jake uses it in the physical sciences world at Diamond in the next talk. Okay, thank you.